Start recording.
I don't know.
Yeah. I was actually afraid of when the first time coming together, I was like, oh no, like, because you know there's a little thing by a dress code, and I'm like, is this the type of place this is? Hey, how's it going? How is Chen?
Oh wow, how are you doing? Upright. Yeah, there is an alternative, but I'm not there yet. But it's very busy.
Yeah.
Yeah. Over a break. I had 2 committee meetings on campus, which I joined by Skype. But of course, there's 12 hours difference. So one of them was Committee on Majors, which meant 3:30 to 5 meeting.
AM for you.
The board of editors and the alumni magazine, and that took 3 hours, 12 to 3. After 2 hours, they took a break, and I lost my connection.
Oh, it's also this, yeah.
I haven't written my talk for AS. Working with us like with Big Zoom, trying to get that. I'm hoping to send it to Ransom Catholics on Friday. Got tomorrow. Yes, I know. Never a dull spot.
Yeah. I'm sort of the same. October is like the October hotel.
Yeah. Fall is always hard.
Yeah, like I think maybe the fourth year, my fourth year here is like this year's this, but like that was I thought this is time. This is me.
That went fine.
Oh, good.
Yeah.
Excellent.
Our busy but good.
So did you get your welding checks or? You know, the one that we have.
Oh, for Tarek, yeah.
You guys are rich?
No.
It's personal.
But it's
Did you get something more recently or?
no, just
Ages ago?
no,
Okay, so I've got I got one before.
we did. I forgot. So this is my first one. Maybe
Maybe they're just catching up.
I don't know. Anyway,
Anyways,
it's the first royalties I've ever had on, I don't know, 8 or 9 patents. You know, but that's good because I never expected any.
well, Zach's gonna got one going on this, so.
Oh, yeah.
Not on what it's
Works
talking about
out.
right now, but on hydrophobic.
Yeah, I have to get back to what you mentioned about that in my vacation.
So I think in this case, well, they haven't done anything with it, but they just logged on. Assume that they could value.
I see.
But so like they paid a $10,000 royalty, but of course.
Just to look at it?
Pardon?
Just to look at it? Wow.
But then the university took $1,000 and then they took half of the
Okay, yeah, I was like, if they only took 1,000, I'd be very surprised. They took 60%. Okay, that's reasonable.
Then after that, there was 4,500 left, and they divided it into 203.
Yeah, let's go, sure, now. Do you have to pay money?
They start being $100,000.
Well, yeah. Do you have to pay money to, like, upkeep? No, so that's pretty good.
That's the reason they don't always file it, because unless they can do a study that's just right.
That's a significant investment.
That's right. So that's the reason they don't patent everything you send over there.
Yeah, so make sure you're actually invested in your investment.
So I didn't finish this on the plane, and I didn't get back. I'll send you what I got. About half of it.
Sure.
And I will finish it.
What's your overall feeling on it?
I find lots of things.
Sure. Yeah, just I mean, the good thing is, so I'm not going to rush. So I'm graduating in yeah. So there's plenty of time. Yeah. So I'm not so just stressed out.
Well, I won't be exactly. Because I want to figure out I don't know. Just after playing good, something went wrong. Shortage of
I'm impressed you can do anything. I'm sorry. I'm like at the
and then you can actually get flat.
Yeah, that's what I tried. You like it, Lance? You've done it before. Yeah, I'm still a novice.
It's 14 hours.
No, not 10:30 yet. Some people. Looking at the. I was waiting to see whether Ben and Pat could come in.
Oh, no,
Too bad. Anyway, I hope they come to
Ben said he had something at 11. Which is good.
Okay. Thank you all for coming to the defense of Zachary Fishman. He's going to be talking to you today about his work on 2D nanosheets of cupric oxide and iron oxide. He's not going to talk about everything that he's done. He's done a whole lot more. And in fact, he's looking at a patent on hydrophobicity of functionalized copper oxides. And he's gratefully staying with us to be a postdoc with Professor Shu Hu. And so we're going to see a lot of him.
Thank you, Lisa. thank you all for coming. Thank you all for tuning in. You've all made incredible time getting here. Whether it took you a few minutes or a few hours, it took me years. This is the Becton seminar room. And there's a joke about the Becton seminar room, because a lot of people give presentations, PhD defenses, and speakers in here. And it's how do you get to the Becton seminar room? And the answer is research, research, research. And so today I'll be presenting some of my research on tuning the optical and catalytic properties of copper oxide and iron oxide nanosheets for CO2 conversion. So, I'll have to turn this on. So 4 years and several projects ago, I was a second-year graduate student, and I had no funding, no papers, and no idea what I was doing. But luckily, Lisa was putting in for a grant for studying copper oxide nanosheets for superconductivity. And I was doing my best to help out. And she would email me, this or that, and say, oh, can you write me a few words on this, or a few sentences on this? And one email I remember in particular, she asked me, it was like maybe midnight or something, and she said, what is the band gap of copper oxide? Very simple question. And it would take me about 2.5 years to just begin to answer it. But let me back up. What is a band gap? So in a semiconductor, you have electrons, and they can be at different energy levels. So imagine you're on a ladder, and you have hands on your rungs. Where your hands are in the ground state, where the electrons are in a semiconductor, that's the valence band, the highest kind of occupied state for electrons. The next rung up, where your hands could go, or the electrons could go, that's the conduction band. And in between, just like on a ladder, you can't put your hands in between the rungs, the electrons can't be there either. This is called the band gap. The difference in energy between the conduction band and the valence band. This is important because to move up from the valence band to the conduction band, you can take in energy. An electron can move up from the valence band to the conduction band, for example, by taking in light, a photon. But only if that photon has the correct amount of energy, if it has more greater than the band gap. This is particularly important if you care about using sunlight. Sunlight, photons, different energies. So if you're using your sunlight to drive a current, such as in photovoltaics, using your sunlight to drive a chemical reaction in photoelectrochemistry, you have to know what your band gap is and what band gap you want to match the energy of the solar spectrum. So for example, silicon, common solar cell material, has a band gap of about 1.7 electron volts. So it absorbs everything higher energy. Another material, cadmium telluride, 1.5 electron volts. It absorbs even more. This new material, copper indium gallium selenide, that's being explored for solar cells, it can absorb even more. Now, you might be noticing a trend. Why don't we have the smallest band gap possible or no band gap at all? Because absorption is not the entire story. You also have to consider recombination. So when you promote your electron to the conduction band using a photon, it doesn't have to do what you want it to do. It can drop back down. It can drop back down, emit some energy in the form of a photon, so some light, or it can emit heat, which is not useful for your system. And it turns out that this rate of recombination, the rate of dropping back down, is dependent on the band gap. If the energy of your photon is much higher, greater in energy than the band gap, it drops back down really quickly. So you want to balance the band gap in terms of absorption and recombination. Shockley and Kaiser studied this, and they found that the optimum band gap for absorbing light with a lot of other stipulations for a solar cell is between 1.2 and 1.4 electron volts. So this is kind of our first reason we want to maybe tune the band gap, or we care about band gap at all. The second reason is if you want to do photoelectrochemistry, you want that electron to power a reaction, you have to consider the energy barrier to that reaction. In water splitting, there's a certain energy barrier. You have to overcome it with your electron in the conduction band, and if you can't, then you're not making use of the electron. Further than that is if you have two different competing reactions, for example, CO2 reduction versus water splitting, both of these reactions compete with each other. And by tuning your band gap, you're tuning kind of the energy of this electron, once promoted, to decide which reaction it would rather favor. So we have two kind of reasons we might want to tune the band gap of a material. How do you do it? This is the first time that nanomaterials kind of come in this talk. So what is a nanomaterial? A nanomaterial is a material that when you zoom in on it really high, it has a nano dimension. One of its dimensions is on the nanometer length scale. A nanometer is 1 billionth the size of a meter. It's about 1,000 times smaller than the width of a human hair. So really small, you can't see it. But if you use a really high powerful microscope, you can see what the shape is and the size. Here are two examples of nanomaterials. Cadmium sulfide, cadmium selenide. When you get down to the nanoscale, size matters a lot in terms of properties. By changing the size, so these researchers changed the size of cadmium sulfide nanoparticles, and they measured their UV vis and photoluminescence. Those are kind of ways to measure band gap. And it equates to changing color, essentially. So you change your color, you change where you emit, you change where you absorb light, change your band gap. Besides nano size, the shape also affects your nano shape. Before I showed a density of states versus energy for a 3D material. There's also changes that occur when you go to a 2D material, 1D material, and 0D material. So nanosheet, nanowire, or nanotube, nanoparticle. A nanosheet looks very similar. These are step functions. Imagine you're changing the size of your rungs on your ladder. So these are still pretty fat rungs. You absorb things above and below the band gap. Or not below, sorry, above an energy band gap. And you still get the benefits of a 2D material. Typically 2D materials are more reactive, have higher surface areas. But say you don't want those extra states, might want to consider a 1D material. These rungs are much thinner. They can't have as many above the band gap energy. And for 0D, this is even more true. So two things to keep in mind. You want to keep in mind nano shape and nano size when you want to think about how you choose this band gap. The structure, it's important. Let's get back to the story. Band gap of copper oxide. So, I woke up the next morning after receiving the email from Lisa, and I decided to do a literature search because I'm a good graduate student, second year, I want to impress my advisor, and I found a couple of sources that said the band gap of copper oxide is 1.2 electron volts. But I was reading over the paper and I noticed that, they said it in the introduction, and that means they didn't do the experiment. So I figured, if I was doing an experiment, I'd want someone to cite my experiment and not cite people who talked about my experiment. So I decided to go to the source. It's a paper by Mirabelli et al. In 1995. They took single crystal copper oxide, UV vis spectroscopy, that's a way of measuring band gap, and they did a temperature dependent study. And at room temperature, they found the band gap of 1.2. Great. But I just wanted to make sure. I wanted to get one more source. Maybe who knows what they're doing. Found another source. Said the band gap of copper oxide is 1.4 electron volts, plus or minus 0.3 electron volts. And they used oxidized copper circuits. So they heated copper and oxygen and made copper oxide and did ultraviolet photo emission spectroscopy. Different way of measuring band gap. But this is a pretty big range. 1.1 to 1.7. That's basically all the materials I showed before. Okay, I'll get a third source to put an end to this controversy. And I found 1.9 electron volts. And if you do another source, I got 1.7 to 2.4. And it went on and on and on. And there were lots of different band gaps in the literature. And no one was really talking about it. It was an unspoken controversy. And by the way, it's not just band gap that is one of these properties for copper oxide. If you look at the catalytic catalysis literature for CO2 reduction, copper and copper oxide is used a lot for CO2 reduction. They're getting lots of different selectivities, conversions, different products, depending on kind of their treatment of their copper oxide, how they make it. But there's a little bit of a lack of characterization. What about their treatment is changing the material? At least they talk about that this is a problem. They know that they're getting different things. So what did I do? I emailed Lisa back and I said I didn't know. I didn't know what band gap of copper oxide is, but those other people didn't know either. So I emailed that, I sent her all my sources and she put it in the grant. She said, great, thanks. And we sent it away and we waited. Waited to hear back. And while we waited, I did some experiments. First thing I did is I optimized my synthesis of copper oxide nanosheets. I wanted to do nanosheets for a few reasons. First, in the grant, superconductivity is important. We thought the nanosheet system would be good for that. Second, Nanosheets are not as well studied. So we're kind of like on the edge, and we're doing something new, which is nice. Third, we weren't so caring about the size of the rung being really small. We didn't care if we absorbed a lot for our applications, as long as we met some minimum criteria. So going back to the nano shape versus density states problem. And so for all those reasons, I decided nanosheets is the way to go. So to make copper oxide nanosheets, it's not actually that hard. What you need first is a copper source, so I use copper nitrate in water, a base, sodium hydroxide, and a surfactant, CTAP. Surfactant, that's soap. It's got a hydrophobic end and a hydrophilic end. That's why it's really good as a soap. It takes off grease because grease is hydrophobic, and water is hydrophilic, so it just comes right off. We use this here for a different purpose. It acts as a scaffold or a soft template for the synthesis. So when you put a surfactant in solution, the hydrophobic parts in a water solution, they hide. They don't like interacting with the water. And so the hydrophilic part points outward. What's going to happen is we're going to try to attract the copper to the surface of this surfactant, this scaffold. But you might have noticed that this is a positively charged surfactant. Why would you use a positively charged surfactant to attract copper, which has +2 oxidation state? This is where the base comes in, sodium hydroxide. When you have copper hydroxide, copper in a basic environment, it forms a hydroxide intermediate. It's copper hydroxide, negatively charged, good. It attracts to the positively charged surface. And since you're attracted there, that's where the reaction occurs when you oxidize it. When you heat it up, you restricted the growth in one dimension, so growth occurs in 2 dimensions, and you get a nanosheet. Second thing I wanted to do was measure the band gap of these materials. I had a new exciting thing to do. Learned UV-vis spectroscopy. This is a very common technique. What it is, people like it because it's easy, it's cheap, doesn't take a genius to do it. So what it is you shine a light on your sample, you measure and you have a detector behind it, and whatever gets through, you measure, and whatever doesn't get through, you don't measure. So as a function of wavelength, this is from a different paper, what you find, you can get absorbance depending on wavelength. And what you do after that is to get band gap from this, you have to do a conversion developed by the scientist Tock in 1966. And it actually makes it really convenient to find band gap. You extrapolate down the linear region of the plots down to the x-axis. And where it intersects, that's your band gap. Pretty simple. The third thing I wanted to do, before I get to that. So I did it on my samples. I made 5 different copper oxide nanosheets, all the same way, different batches, and I got 5 different band gaps. That's good and that's bad. It's good because, well, everyone else was getting different band gaps, so I was reproducing their irreproducibility, which is great. It's kind of bad because maybe I'm incompetent, I just can't measure something. But then I did it a few times on each sample, and I could actually measure the same band gap for the same sample. So that was good. So there is a real weird difference between these. That's our first mystery. But I didn't want to get to that mystery yet. I wanted to check out my new reactor. So a reactor is like a chemical engineer's best friend, at least if you do catalysis. And what it is, it's basically a fancy oven. You can heat something up, and you can pass a gas over it. And what I want to do with my system is heat up copper oxide, because I had copper oxide, and see what happens. So I heated it up. So here's an SEM image. These are SEM images, standing electron microscope images. These are the fancy microscopes, so you can see nanomaterials. And these are nanosheets heated to 300, and they look very similar to nanosheets unheated. They're the same. So heating it to 300 doesn't really do anything. Heating it to 450 Celsius does do something. You start to get these rounding of the edges. You start to lose your structure at 450. At 700, your structure's gone. 900, you got this other weird, bulk material going on. This is nothing new. People knew about this for ages. It's called sintering. When you heat nanomaterials up, you lose structure. But I saw it with my own eyes, and I thought that was pretty cool. Good news. The grant came through. Hooray! I won't be presenting on this if it didn't. Probably. And that's when the work really started. So I wanted to take, I could have started looking into superconductivity, but I was really more interested in this band gap and reactivity differences that was going on. And I wanted to really plunge into this discrepancy in the literature. So I devised an experimental plan based on what I knew. It could have been from structure that these differences were changing. It could have been from composition. Maybe it's different, not copper oxide anymore, but maybe it's a structure problem. Maybe it is copper oxide, but just different structures. So I knew how to change the structure. I just heated it up a little bit. I knew how to measure band gap, and I had a reactor, so I could measure reactivity. So my hypothesis was, I think that heating will cause some structural changes, and that these changes will cause changes in the band gap and the reactivity. I was going to heat to not so hot temperature. I didn't want to kill the structure, so I heated to 350 Celsius. That's in between at 300 where nothing happened and at 450 where too much happened. And I heated it for different amounts of time, 30 minutes, 60 minutes, 120 minutes, in oxygen, because I didn't want to change the composition. I wanted it to still be copper oxide. Copper oxide, cupric oxide is the most oxide of copper that you're going to get. I thought. We can get back to that a little later. So that was the plan. Then I was going to measure the band gap using UV vis and the reactivity using TPR. I'll get to what TPR means in a second. So I did that. And what I found was that the band gap does change if you heat up these structures in oxygen. At the untreated sample, I found was 1.53 for this particular sample. I took that same sample, heated up to 350 for 30 minutes, and it was 1.75 electron volts. Heated for an hour, 1.86, and then it comes down a little bit, 1.82. It's up, and then down a little bit. I was excited. Something I did worked. Hooray. I showed it to Lisa. She was interested, excited, great. I showed it to Gary, and Gary was also interested, but this is the first time I learned something about professors. Is when you show them something cool, they say, go do it again. So I went and did it again. I got a very similar result. But then he said, do it again, but this time, does it have to be in oxygen? Can you do it in an inert environment? And I thought about it, and it's like, what's going to be the difference? There shouldn't be any difference, right? Maybe the inert, maybe you change the composition, maybe you'll see bigger change. This is where I learned the second thing about professors, is that they're usually right, you should listen to them. Because heating up in an inert environment doesn't change the band gap. So you'll notice that the initial band gap is different. These were two different samples, the red line and the black line. So back to our other mystery, why different samples have different band gap. But heating them in oxygen changes the band gap, while heating them in inert doesn't change the band gap. Second mystery. But I wanted to go play with my reactor. I had, my hypothesis. I found changes in band gap. Second piece was changes in reactivity. So I did something called TPR, hydrogen TPR, to test the reactivity. This is a probe sort of reaction. Copper oxide is a mild oxidizing agent. Hydrogen is a strong greasing agent. When you heat up copper oxide in hydrogen, the hydrogen sucks out the oxygen from the copper oxide. But depending on what temperature, you can see how reactive your material is. So I use mass spectrometry. This is you're measuring the content of your outlet gas based on the mass of the different components, mass to charge ratio. So you can kind of piece out what's there. So if I'm measuring hydrogen and I'm heating up my reaction, over time, at one point, it's going to start reacting with my material. I'll get a dip in the hydrogen signal, and then I will eat up all my hydrogen and all my oxygen material, and then I'll go back to my normal hydrogen level. So on the mass spec, it kind of looks like this. So I plotted hydrogen consumption, so the reverse of that, on the y-axis, and temperature on the x-axis. And these are the different points at which you start to consume that hydrogen and form water. If you notice the untreated sample in red, that reacts at the highest temperature. Least reactive. You have to put more energy in to get it to react. As you go to the treatments, the 30-minute treated sample becomes more reactive. It reacts at a lower temperature. 60-minute reacts at a lower temperature. And then 120-minute, it comes back a little bit. Very similar trend to the band gap. Band gap increases, reactivity goes up. Decreases a bit, comes back down. Second piece of information you can get from this is if you look at the area under these curves, you integrate them, you can get how much hydrogen was consumed, total. And that should be equal to the amount of oxygen that was in your material. And what you would expect for copper oxide, so I loaded a known amount of copper oxide, so I know how much copper was there. What you would expect for copper oxide is 1-to-1 copper to oxygen. But what I found was actually, in these materials, it was 1 to 1.25-ish. Too much oxygen. Maybe it's on the surface. But even stranger is it doesn't really follow the same trend. The untreated has the most. But if we were to ignore the untreated, which you can't really do, but just for the sake of this, if you were to ignore it, it kind of then follows the trend. It goes up and then comes back down a little bit. We'll keep that in mind for later. It's our third mystery. But I was really interested in my hypothesis. I thought these mysteries, yeah, they're mysteries, but I want to get my paper out. Let me finish my hypothesis. The last piece of the pie, the dotting the I's and crossing the T's, was I wanted to make sure the structure changed. That was the goal of this. Change the structure, you see the band gap change, the reactivity changes. So this is the untreated sample. Very pretty copper oxide nanosheets, gave me their best side. 30 minutes? Well, they were still nanosheets. There wasn't really any structural change to them. Okay, what about the 60-minute? No, they're still nanosheets. This is where I started to get a little panicky. Because the 120 minutes was also nanosheets. There was no structure change. No structure change, but I'm seeing property changes. So what's going on? All right, maybe I shouldn't be changing the composition, but maybe I'm changing the composition somehow. So I did, I forgot. So instead of another technique to measure kind of structural changes, I did BET, which is a surface area change, surface area measurement. And maybe there was a little bit of surface area change, but not any trend, not really anything to write home about. It's very small, if anything. So I concluded that the treatment was having no effect on the structure. Okay, let's get to the composition. So the composition, to test that, I did XRD, X-ray diffraction. Copper oxide's nice. One crystal structure, one composition. Not very nice in my case because they all look the same, so I'm not changing the composition. Everything was very much alike. You can tell because the more than the intensities, the locations of these peaks are in the same place. That means it's the same material, basically. So now these mysteries have started to pile up, and I was in over my head. Didn't change the structure, I didn't change the composition. As an experimentalist, you're kind of in the dark here. What do? I did what any good experimentalist does. I talked to computationalists. So collaborators in the Batista group, Dr. Batista up on Science Hill, were kind enough to model a copper oxide nanosheet in their computer. And then what we did is we removed some copper atoms from the surface and used their theories, their programs, to measure the band gap of this theoretical material. Why are we moving copper atoms? We're moving copper atoms to simulate an oxygen-rich surface. We just saw before that there's a higher amount of oxygen than copper, so maybe this is a regime we should be dealing with. We remove 0 copper atoms, 8 copper atoms, 16, increasing amounts of copper atoms. That leads to an increasing proportion of oxygen. And what we find is that the band gap does increase, quite drastically. That's good. That answers a little bit of that mystery of the TPR. But remember, the untreated sample had the smallest band gap but the most oxygen. So this can't be everything. The second thing we investigated, and a very important thing, is we changed the way we remove the copper atoms. So in the last one, we removed the first atom in the first row, the second atom in the second row, the third atom in the third row. In this, we did different ways of removing them. We removed the first one, the regular pattern, but then we also removed them in rows at a time, adjacent rows, alternating rows. We did a patchy area pattern removal. And what we find is that your band gap does change when you do this different sort of removal. let's talk about these different strategies of removal and how they might have some physical realities to them. I like to call the regular and the areas ones, those two types of removal, they're diffuse removals. I consider them high entropy removals, in quotes, very disordered sort of removals. They're diffuse, spread out. Orders, rows at a time, that's a low entropy. That's a very ordered arrangement of removing things. Where would you expect regulars and areas? You might expect it when you heat up your material and things are mobile, moving around. Things have a chance to spread out. You might expect the adjacent and the alternating rows ones to be in a solution where things are kinetically trapped. So this might address a few mysteries. One, why are all the untreated samples different? Well, because in the kinetically trapped state, your band gap can vary a lot. Second, the untreated sample will have more oxygen but a lower band gap. Well, it varies a lot. It could be below what we wanted, what we thought we would have. But as an experimentalist, I'm not satisfied with just computations solving everything. I need to verify the computations in some way. So I needed an experiment that would kind of get at the root of this. And it seemed like the question of can this happen is founded on can oxygen move around on the surface, can it exchange with the gas phase? Because if it doesn't exchange with the gas phase, then that mystery of the oxygen versus the inert treatment doesn't make any sense. So I devised an experiment. I thought that this oxygen exchange between the gas and the solid phase is really important. And if it's not happening, then I don't believe it. And if it does happen, then I do believe it. So I did something called isotopic TPO, temperature programmed oxidation using O18, oxygen. O18 is an isotope of oxygen. It has heavier weight. Heavier weight looks different in the mass spec, so you can differentiate it between O16. The only source of O16, normal oxygen, is in the copper oxide nanosheets. The only source of heavy oxygen is in the gas phase. So if I see a molecule in my mass spec that has one of each atom, then I know exchange had to have occurred. It's the only way that you get that. So I did the experiment, and that's exactly what I saw. Just around, at temperatures above 325 C, you start to see this trace in the mass spec of a molecule of oxygen that contains one O18 atom and one O16 atom. So what is the band gap of copper oxide? It depends. It depends on the amount of surface oxygen, so more oxygen, bigger band gap in general. But you also have to consider the surface oxygen distribution. So more ordered arrangements leads to more variation. And the third takeaway I want you to get from this is that in this system, copper oxide nanosheets, the band gap and the reactivity were correlated. When you go up in band gap, you went higher in reactivity, so lower temperature in reacting with the hydrogen. Does this solve all the problems in the literature? No. I'm not saying that this is why everything is kooky. I'm saying that this might be one reason. Let's take a breath. Get a drink of water. I'd like to go back to my second year, just for the story now. Because I really liked my second year. I had a lot of freedom. I was in an old lab. I get to play with things. A lot of stuff just lying around. I would come in some days, I would just mix copper oxide with stuff. One thing I remember mixing copper oxide, I mixed it with ammonium hydroxide, NH4OH. And when you mix it together, you completely dissolve all your copper oxide, it eats it all up. You have no more nanostructure. It's very sad for the copper oxide. It becomes copper ions in solution, but you get a nice blue color solution. It doesn't do that to other things, just copper things. Anyway, I thought that's neat. But I would mix it with other things, and one thing I mixed it with copper oxide with was ferrous sulfate, Fe. Where is it?
Fe plus 2, or 2 plus.
Ferrous sulfate. And if you mix it with ferrous sulfate and you heat it up, your solution turns orange. And chemists and chemical engineers get excited about color changes because it means something happens and you can see it. It's kind of cool. And when you mix copper oxide nanosheets with other sorts of salty solutions, you don't get this. It just nothing happens. It's kind of boring. So I was excited about the ferrous sulfate. And I learned from my last time, So I did it again, and the same thing happened, which is good. And then I took it down to the TEM, the transmission electron microscope. It's another type of microscopy technique. And what I found was that there were nanosheets in my nanosheet sample, different nanosheets. Ones that had iron in them. But they were separate than the ones that had copper in them. So in this image, if you can see, these kind of hard-looking structures, that's the copper, so that's in red. And then kind of this wispy outline is in blue. That's the iron. So you have these wispy kind of nanosheets that are iron and the rigid ones that were copper. Well, that's weird. I didn't add iron nanosheets to my sample or something like that. So it must have popped up. So this is the story of a happy accident of hard templating iron oxide nanosheets. Interestingly, I looked in the literature, no one really made iron oxide hematite nanosheets that thin before. I didn't say these were hematite yet, but if I could make hematite nanosheets, that would be pretty important. So, the last project was an investigation. I'm rooting out what's going on. I'm on the edge of science. I'm exploring something new. Different sort of mindset. But to measure these new properties, first I have to figure out what the hell is going on. Why does ferrous sulfate work? I tried ferric nitrate, so something with Fe plus 3+. That didn't work. So it's not just iron does this. There's something special about ferrous sulfate. And if you look up what ferrous sulfate is, it's a mild reducing agent. Copper oxide is a mild oxidizing agent. The last part, we know what happens when you mix oxidizing and reducing things. You get redox occurring. So what I think was happening was this Fe plus 2 is binding to the surface of copper oxide, and then it's being oxidized. If it's being oxidized, and the redox is occurring, it's only happening on the surface of the copper oxide. Similar to before, how we had the oxidation only occurring on the surface of the soft template. Now it's occurring on the surface of the copper oxide. I got some help from molecular modeling people, Victor Batista's group, and they showed that the binding of this iron complex to the surface is favorable. It's good. So there's some credence for this. It's not just me, saying stuff. I want to draw a distinction between this, what I'm doing here, and what I did in the last work. In the last work, to make copper oxide nanosheets, I used a soft templating method. There's surfactants, self-assembles in the solution. A lot of people do this sort of thing. And the reason they do it is because you can make a lot of different structures using it. A soft template is very changeable. You can change it based on the solution environment. Change the pH, change the temperature, all these things change the structure of the soft template. Change your structure. However, if you notice, those things that change the structure of your soft template also affect the kinetics of your reaction. So it's really hard to study the kinetics of your reaction in these nanostructure synthesis. And it's also sometimes hard to get a particular nanostructure because you're changing two things at once, basically. Growth rate, growth parameters, and also structure parameters. And growth parameters affect structure parameters. Hard templating is slightly different. Hard templating, I put copper oxide in solution. In water, it doesn't really change that much. It's still copper oxide. And you can do reactions, change the temperature and stuff like that, the kinetic parameters, without affecting your hard template. So you can study these things and possibly access new nanostructures you wouldn't have otherwise been able to get. But the only downside is it's typically hard to remove these hard templates. So if I want to study these iron, whatever nanosheets, iron hydroxide or iron oxide, if I want to get hematite and study that, I have to get rid of the copper oxide somehow. So how do I get rid of copper oxide and not the iron? Well, I just remembered that the ammonium hydroxide really loves copper oxide and dissolves it. Makes a nice blue solution. So if I rinsed my mixture in ammonium hydroxide, got the nice blue color, and I was left only with my iron hydroxide, heat it up to iron oxide. Hematite's the most stable form of iron oxide. It's pretty easy to get if you just heat it in air, heat it in oxygen. Short time, you don't want to kill the structure. So I did that. Had some nice, by themselves, hematite nanosheets. They were polycrystalline. They were pretty thin. They were about 4 to 7 nanometers by AFM. I wanted to compare in this work how they look compared to other dimensions of hematite. Nanowires, nanoparticles. So got some collaborators, Julie Zimmerman's lab. Amanda gave me some very nice nanoparticles. Julian made some very good hematite nanowires and optimized the nanosheet synthesis. And we were all set. But I didn't want to be fooled like last time, so I wanted to do all my characterization up front. So I did the previous slide was TEM and SEM for the structure, and this slide is the composition. I wanted to make sure they were actually hematite, not just me saying it. And so the three to kind of focus in on are the nanoparticles, the nanowires, and the nanosheets of hematite. Those are the finals. These are the before products. And the important part is that all of these peaks are in the same spot. That means it's hematite. But something to notice and keep in mind is that the relative intensity of peaks may say something about what facet of the material is exposed more. This is like you cut an onion in half, but you can do it in different ways, and you see like a different shape on the inside. Different facets could have different reactivities. So interestingly, the nanoparticles had the 104 facet was more expressed than the 110, whereas the nanowires and nanosheets, the 110 was more expressed. Is it important? Maybe. Find out later. Did XPS. XPS is another sort of characterization technique. It's a surface-sensitive technique. On the left, this is the iron sort of part of the spectrum. And the important takeaway from this is they all look alike. This is what iron plus 3 looks like. So this is more evidence for that redox mechanism. I put in iron plus 2, I got out iron plus 3. You have to have some oxidation event occurring. Second thing to keep in mind is if you look on the oxygen side of the spectrum, you see, importantly, first is this iron-oxygen sort of binding, very important in iron oxide. The hydroxide also has it. Interestingly, the nanoparticles have this extra hump here, which corresponds to hydroxyls on the surface. And the nanosheets and the nanowires don't really have that. Is it important? Maybe. I was interested in the optical properties and the catalytic properties. So these are things to keep in mind when we're looking at those properties. Maybe that's reasons for these differences in properties I'm about to show you. First difference in property is band gap. So for hematite, band gap doesn't really change depending on your structure as much. And whereas in copper oxide, it's changing all over the place. Hematite's pretty stable. It's about 2.1 or 2.2 electron volts. And for my nanosheets and nanowires, that's about what it is. For the nanoparticles, it was much higher. It actually, the spectrum looked very similar to the hydroxide precursor. And it had a lot of what you call sub-band gap absorption where it shouldn't be absorbing below the band gap. It's weird, if you cut it over here and don't look at this part, but look at this part of the nanoparticles, you'll get a very similar band gap. So the thought maybe is, maybe you have two materials here, hydroxide and an oxide, and the hydroxide is coming from these hydroxyl groups on the surface. Something to think about. To the CO2 conversion. I want to do CO2 conversion because I care about the environment. The way I did it was slightly different than the way a lot of other people do it. A lot of people do electrochemically, photoelectrochemically. I did it catalytically. I did a reverse water-gas shift reaction. You take in CO2 and hydrogen and you turn it into carbon monoxide and water. Carbon monoxide, isn't that supposed to be really bad? It is if you breathe it in. It's actually really helpful if you're making bigger molecules. Fischer-Tropsch reaction uses hydrogen and carbon monoxide together to make alkanes and alcohols and other things. So I booted up my reactor, measured the mass spec for CO2 conversion. And what I found for the nanosheets and the nanowires, they're both really good at converting CO2. The nanoparticles, not so much. Another thing to notice about this is while the nanosheets kind of peak out around 30% and then drop off at around 600 Celsius, the nanowires keep going. They have a little bit of a dip in the same place, but they get up to that 55% at really high temperatures. It's really good. But why? To figure out, gain some insight into this. I did H2TPR, my old friend, temperature program reduction using hydrogen. It's a simplified version of that last reaction. I had hydrogen and carbon monoxide in the last reaction. Now I just have hydrogen. When you heat these structures up in hydrogen, what you find is that the nanosheets and the nanowires are pretty similar. They have both the same peak over here, but they have this earlier peak, and and the nanoparticles take off later. And remember what we said in the last project, if you react at a lower temperature, you're more reactive. Higher temperature, you're less reactive. Interestingly, if you line this up to the CO2 reduction part, this part lines up pretty well with the CO2 conversion. Makes it seem like hydrogen is really important for this process. This reduction event must occur for the CO2 part to occur. The question of crystal facet was one we had before. Is the nanoparticles worse because it's worse at absorbing hydrogen on the surface? We had people in Victor Batista's group, again, model some iron oxide. And what they modeled was the 104 facet versus the 110. And actually, counterintuitively, hydrogen adsorbs stronger to the 104. You'd expect the 104 to be more reactive. And that's not what we're seeing here. So it's not a facet thing. It's the sites of the material are different in some way. Perhaps because of the shape, nanostructure. The second we have to look at is this pre-peak. What does this pre-peak mean? When you have a peak, it means reduction is occurring. If you look in the literature, people don't do reverse Bohr gas shift with hematite, but they do it with magnetite. Magnetite's a reduced form of hematite, and what you find is I took the nanosheets out at different temperatures. 250 C, 500 C, 700 C, to see what was going on. And what you find is magnetite emerges at 250 C. If we go back, the peak is at 225. So right after that peak, now your material is magnetite. Magnetite does do reverse Bohr gas shift. So it seems like you have to go to magnetite first, and then you have this switching maybe that's occurring between magnetite and iron. So if you look at 500, it becomes a mixture of iron and magnetite. And so it seems like it's a balance between reducing with hydrogen and reoxidizing with CO2. And maybe the nanosheets are bad because they're too reactive. They go too much reduced. You can't reoxidize. Maybe they lose structure. And I have, in the supplementary information of the paper, it shows kind of some of the stability aspects to it. You do lose nanostructure. The nanowires are actually better at retaining their nanostructure. There's a balance here, it seems, between reactivity and stability, which is important for reverse Bohr gas shift over hematite, over iron oxide nanosheets and nanoparticles. So what have we learned? General from this project. Hard templating, you can use it to make new materials. It's kind of a new spin on an old technique, not really applied to 2D materials. Now it can be. Second, what you take away from this part, but also in general, nanostructure changes optical and catalytic properties. There's a link, it seems, between these optical properties and catalytic properties in many systems, at least in copper oxide nanosheets and iron oxide nanosheets. And I like to talk about what I've learned from my PhD, just a few things in general. The first thing, it's okay not to know the answer to simple questions. Sometimes nobody knows, no one's talking about it. Case in point is copper oxide bandgap. Second thing, don't be afraid to just throw things in a beaker and see what happens. Never know, be a good project. And the third thing is a good group makes everything easier. Makes the good times better, the hard times much easier. In a PhD, there are going to be good times and there are definitely going to be hard times. Things are not going to work. It's important to have a good group for your own sanity, and it just makes everything easier. And the last thing, before I thank everybody, I want to thank someone who doesn't get thanked a lot. During a PhD, your questions kind of come, like it's a little bit of a battle inside, and your questions kind of turn against you. And one of the hardest parts is like receiving criticism. That's always a really hard part in a PhD process. And especially towards the end, the thought of, what did I actually do? Was what I've done enough? I mixed some things together. I measured a few properties, big whoop, But I did study a lot of properties. And so I'd like to give a shout out to reviewer 3, the copper oxide nanosheet grant. I thought these reviews were terrible, but at least I had a lot of confidence and we ended up getting it soon.
What reviewer 3 said is, indeed, one needs only to review zinc oxide as a prime example of the difficulty of understanding the interplay between vacancies, altered free electron densities, and optical properties. Several years and a couple hundred papers by dozens of groups finally sorted out the effects of oxygen deficiency. The PI grossly underestimates the solid-state physics and challenges of interpretation. Graduate students can earn their degree focusing upon but one property. Hope people agree with that. So with that, I'd like to thank everyone. First, well, let me thank you. First, I'd like to thank the people who gave me money. The research laboratory. Always thank them first. I'd like to thank my committee, my advisor, Lisa. You're probably one of the strongest people I know and the most supportive. You know, this was supposed to be a grant for superconductivity, and I went off and did bandgap and reactivity, and she sends me papers on bandgap and reactivity. It was wonderful. Julie and Gary, your criticism has made my work better, and your interest has made me interested in it also, so I really appreciate it. Your availability to come to DPRs, and this is very important. I'd like to thank my lab members, past first. So my past lab members, you guys were the role models for me, and certainly helped me develop and know what a good researcher is, and a good person is also, and what a good group is. And of course my lab members present. You guys, I can't think about you guys without like smiling and laughing. You guys are really great, and I know you'll go on and surpass me and do very good things. I'd like to thank my collaborators, especially in Victor Batista's lab, Dr. Visa. Certainly helped clear up like lots of mysteries in my work. I don't know if I would have ever had as much insight without their help. And Amanda, of course, for iron oxide nanoparticles and talking about hematite. She is the hematite expert. I'd like to thank all of the facilities at Yale and the people who manage them. All the data, I would have had no data to show if I didn't have them. So I'm really grateful for their assistance and their expertise. I'd like to thank Ellen, Ben, Kara, Melody for making everything easier in terms of administration. So many headaches they've just made go away. It's pretty nice. Be nice to support staff. And then, of course, I'd like to thank my friends and family. My family, endless wells of encouragement and interest in my work. Yeah, they're wonderful. And my friends who I go to India with, my friends who I have potlucks with, my roommates who I go to Six Flags with, and movies and board game friends, and my college friends who come up to visit me, even though I'm far away from them. And I'd like to thank all of you for coming and listening to me ramble for probably too long. And everyone for tuning in. Thank you very much.
Thanks. As a post note, we have gotten some superconductivity with Zach, Julian, and Matthew. Here. So hopefully that pleases the Army Research Lab.
This is not the end. This is just the beginning.
Also, we're going to have a celebration at noon in room 321B. We're now going to dismiss the audience, except the faculty stay, and we should be joining you in 321 shortly. Thanks.
You must be really busy. How are you? Thank you very much.
Hey, how are you doing? That paragraph. So,
Yeah, that's correct. Very good.
I think that was really important.